Okay, so for this video, we will be discussing applications of the derivatives of inverse trigonometric functions. So the applications of inverse trigonometric functions involve maximizing and minimizing angles, as well as finding the rate of change, okay, of angles. Okay, so we will be discussing one example for each. So for our first example, so we have here a maximum minima problem. So the problem goes like this. So the television screen at a sports arena is vertical and 2.4 meters high. The lower edge is 8.5 meters above an observer's eye level. If the best view is obtained when the angle subtended by the screen at eye level is a maximum, how far directly below the screen must the observer be? So here we are asked to solve for the distance, right? So the distance of an observer from a screen so that it can have the best view. So having the best view means that it will have the maximum subtended angle. Okay, so for us to clearly visualize the problem, so let us first draw an illustration of the problem. So obviously we have a television screen, okay, below an observer's eye level. So let's say this is the television screen viewed sideways. Okay, so we have here a side view of the TV, which is 2.4 meters high. So it's a fairly large TV for an arena. So we have 2.4 meters, okay, is the height. Okay, and 8.5 meters below the lower edge. Okay, so where's the problem? 8.5 meters below the lower edge is the eye level of the observer. Okay, so we have here the observer's eye level is 8.5 meters above. The lower edge, okay, of the television is 8.5 meters above an observer's eye level. Okay, so an observer's eye level would be below that. Okay, so let's say we have the observer here. Okay, so we have the observer here. Okay, so the eye level of the observer again is 8.5 meters below the lower edge of the television screen. Okay, so the angle subtended by the screen, okay, with respect to the observer is to be maximized. Okay, So we are maximizing this angle right here. So let's say that is theta. Okay. So what we want to solve is the distance. How far directly below the screen must the observer be? Okay. So we are talking about the horizontal distance of the observer from the um, television. Okay, so that it can have the best view or um, the maximum subtended angle. So let's say that distance is x. Okay, so that distance is x. So for our solution now, or our required first, so our required is x. Solve for x at theta is maximum. Okay, so we want the largest angle. Okay, so at what distance should the observer be positioned so that it can have the maximum viewing angle? Okay, so to maximize theta, okay, with respect to x, so therefore we must have theta as a function of x. Okay, so we must solve for theta as a function of x. Okay, but to solve for theta, okay, as you can see, so to solve for theta, so we need the measurement of this angle, okay, described by the larger triangle, the larger right triangle. So let's say that is alpha, and we must also have the value for the smaller angle, okay, described by the smaller triangle. So let's say that is beta. Okay, so therefore our theta is the measurement of the larger angle, which is alpha, minus the measurement of the smaller angle, which is beta. So we will obtain theta by subtracting those two angles. So theta is equal to alpha minus beta. Okay, so using our knowledge of trigonometric functions, so we will express alpha and beta in terms of x, so that um, so that we can express theta as a function of x. Okay, so as you can see from the triangles, we can use the trigonometric functions, okay, to relate theta and x. Okay, so using the larger triangle, and we have here the subtended angle alpha, so we can see that we can use the trigonometric function tangent, okay, because we are given with we have the two sides of the right triangle. Okay, so our tangent of alpha is equal to the opposite side. So the opposite side is the total of the height of the television and then this length. Okay, so we have 2.4 plus 8.5 as our opposite side, and we have x as our adjacent side. So tangent alpha is equal to opposite over adjacent. So therefore, our opposite side is 2.4, sorry, plus 8.5 over x, okay, or that is equal to 2.4 plus 8.5, that is 10.9, right? So 10.9 over x. So therefore, our alpha is equal to arctan, okay, arctangent of 10.9 over x. Okay, so similarly, we can also do that with beta. So beta is described by this smaller triangle. Okay, so the smaller triangle has a height of 8.5 meters and a base of x. Okay, so this is the opposite side, and then this is the adjacent side. So we can still use the trigonometric function tangent. So tangent beta is equal to opposite 8.5 over adjacent x. Okay, so therefore beta is equal to arctan of 8.5 over x. Okay, so using those two, so substituting alpha is equal to arctan of 10.9 over x and beta as arctan of 8.5 over x. So therefore, we now have the function, we have now theta as a function of x, for which this is arctan of 10.9 over x minus arctan of 8.5 over x. Okay, so now we can now derive theta with respect to x. Okay, so getting its derivative and then setting it to 0 so that we can solve for the maximum value of x. So setting d theta over dt is equal to 0. So let us solve for d theta over dt. So from here, so we recall that the derivative with respect to x of arctan of u is equal to, from the formula, it's 1 over 1 plus u squared multiplied by du over dx. Okay, so our u for the first term, in this case, our u is 10.9 over x. Okay, so deriving arctan of 10.9 over x following this formula, so we will have 1 over 1 plus our u from the formula is 10.9 over x, okay, multiplied by derivative of u with respect to x. So the derivative of 10.9 over x, okay, so we can use the power formula, so it will become this will become 10.9 x raised to negative 1, right? So using the power formula, so multiplying the exponent and the coefficient, so we will have negative 10.9, okay, x raised to negative 1 minus 1. Okay, multiplied by the derivative of x with respect to x, that is 1. Okay, so minus, so similarly for arctan of 8.5 over x, so we will have 1 over 1 plus u squared. Our u in this case is 8.5 over x. Okay, so multiplied by, so similarly with what we did here, 8.5 over x is equal to 8.5x raised to negative 1. So deriving it, so multiply the exponent to the coefficient, so we will have negative 8.5 x raised to negative 1 minus 1 multiplied by the derivative of x with respect to x, so that is 1. Okay, so next step is to simplify. So simplifying, sorry, so this is dx. Okay, so d theta over dx is equal to, so simplifying this, this will become 1 over 1 plus 10.9 squared over x squared times, this will become negative 10.9 over x squared minus, so we can have negative times negative, so that is positive, so plus 1 over 1 plus 8.5 squared over x squared times, this will now become 8.5 over x squared. Okay, so next we can now multiply numerator times numerator, denominator times denominator. So this will become so 1 times negative 10.9, so it's negative 10.9. And then we distribute x squared for each of the terms in the denominator. So 1 times x squared, so that is x squared plus 10.9 squared over x squared multiplied by x squared. It will cancel out x squared, so what will remain is 10.9 squared. Okay, so let's do that on the second term also. So 1 times 8.5, that is 8.5. Distributing x squared in the denominator, so 1 times x squared, that is x squared plus 8.5 squared over x squared times x squared, so that is that will cancel out x squared, so what will remain is 8.5 squared. Okay, so next is we can add the two fractions. Their lowest common denominator will be their product, because that is their LCM. So x squared plus 10.9 squared times x squared plus 8.5 squared. Okay, so the LCD divided by this x squared plus 10.9 squared multiplied by negative 10.9. So dividing this with this, it will cancel out x squared plus 10.9 squared. So what will remain is x squared plus 8.5 squared, and then multiplying that by negative 10.9. So it will become negative 10.9 times x squared plus 8.5 squared. Okay, plus, so similarly, so this divided by x squared plus 8.5 squared, it will cancel out x squared plus 8.5 squared, and then what will remain is x squared plus 10.9 squared, and then multiply it by 8.5. So what it will look like will be 8.5 times x squared plus 10.9 squared. Okay, so next is, since this is equated to 0, okay, so d theta over dx is equated to 0, so therefore this is equal to 0. Okay, so when we cross multiply the denominator with 0, so what will actually remain is only the numerator. Okay, so we can now forget about the denominators because it will be cancelled out by cross multiplying it with 0. So what will remain is the numerator. So simplifying the numerator, so we will have 10.9. So we will distribute. So 10.9 x squared plus negative 10.9 times 8.5 squared. Okay, plus we have 8.5 x squared plus 8.5 times 10.9 squared. So that is equal to 0. Okay, so simplifying, negative 10.9 x squared plus 8.5 x squared, so that is negative 2.4 x squared, right? And then adding the constants using our calculators. So apologies for the very old calculator. So we have negative 10.9 times 8.5 squared plus 8.5 times 10.9 squared. So that will give us 222.36. So plus 222.36 is equal to 0. So solving for x, we can transpose this on the other side. So negative 2.4 x squared is equal to negative 222.36, dividing both sides by negative 2.4, negative 2.4. So we will have x squared is equal to, so negative 222.36 divided by negative 2.4. So we will have 92.65. So therefore, extracting the square root of both sides, x will now be equal to positive or negative 92.65. Okay, so for which we will have two roots, x1 and x2. So x1 is the positive square root. So square root of 92.65, that is around 9.625. Positive 9.625 and negative 9.625. Okay, so but obviously x is distance, so therefore it's we will only take the positive value of the root. Okay, so therefore x is equal to 9.625 meters. So therefore that is already our answer. Okay, so that is the required distance, okay, from the observer to the screen. That is the the horizontal distance. Okay, so the horizontal distance okay, so that should be its distance so that it can have the maximum viewing angle. Okay, so as a review to our solution, okay, so the key here is to express, okay, so theta as a function of the unknown. Okay, so you always express the variable you want to maximize, okay, in terms of the other variable. Okay, and then get its derivative and then set it to 0. Okay, and then here, so we have divided triangles into two parts, the smaller and the larger triangle, so that we can use the relationships using the trigonometric functions. Okay, so that's it. Okay, so for our second example, so we have here a problem involving the rate of change, okay, or time rates. So we have a winch on a loading dock is used to drag a container along the ground. So the winch winds the cable at 2 meters per second and is 5 meters above the ground. So at what rate is the angle between the cable and the ground changing when 10 meters of cable is out? Okay, so to help us visualize the problem, again, we need to illustrate, we need to draw the diagram of the situation given. So let's start with the first sentence. So a winch on a loading dock is used to drag a container along the ground. So we have a container along the ground that is being dragged. So we have, let's say this is our ground. Okay, so we have a container. Okay, and then we have the winch winds the cable at 2 meters per second, and the winch is 5 meters above the ground. Okay, so maybe our winch is somewhere here, 5 meters above the ground. Okay, so it is connected to our container using a cable. Okay, and this is 5 meters above the ground. Okay, so this is being wound. Okay, so this is turning. So the winch is turning so that it pulls the cable, okay, at a rate of 2 meters per second. So this is actually turning. Okay, so by turning that, so it will pull the cable so that the container will be dragged across or along the ground. Okay, so yes, that's it. So we are given that the cable is being wound at 2 meters per second. Okay, so let's say this length is x. Okay, so if that is our x, so therefore our dx over dt, or the rate of change of the length of the cable, is 2 meters per second. Okay, so but we have to be careful of the signs, okay, of the rate. So we have to be careful of the signs. So we must consider what is actually happening to the physical quantity being represented. Okay, so we have the physical quantity being represented by x is the length. Okay, so as you can see, what happens when the cable is being wound, so what happens to the length is that it shortens. Okay, it decreases. The length of the cable decreases. Okay, so therefore our rate must also be consistent with what is happening. Okay, so therefore, since the cable is shortening, therefore dx over dt must be negative. Okay, negative 2 meters per second. Okay, so for the required in the problem, so we are required with the rate of change of the angle between the cable and the ground. Okay, so this is the cable, this is the ground, so therefore we must be looking for this rate of change of that angle. Okay, so for our required, is d theta over dt. Okay, at the condition given is when 10 meters of cable is out. So that is at x is equal to 10 meters. Okay, so solution. So we must obtain theta as a function of x. Okay, so as you can see, we have here obviously a right triangle. Okay, and then we have the opposite side of theta, and then the hypotenuse. Okay, so the trigonometric function that would be most suitable will be the trigonometric function sine. Okay, so sine of theta is equal to 5 over x. Okay, so therefore theta is equal to arc sine of 5 over x. So now we express theta in terms of x. So now let's derive it with respect to time. So we need to find d theta over dt. Okay, so this now will be, so recalling the formula, so with the derivative with respect to x, okay, of arc sine of u is equal to 1 over square root of 1 minus u squared times du over dx. Okay, so in this case our u is 5 over x, so therefore we will have 1 over square root of 1 minus 5 over x squared multiplied by the derivative of u with respect to x. So derivative of 5 over x with respect to t. Okay, so we will be using the power formula. So this 5 over x is actually equal to 5x raised to negative 1. So similar with our first example, so deriving this, so multiplying the exponent by 5, so we will have negative 5 x raised to negative 1 minus 1 multiplied by the derivative of x with respect to t, so that is dx over dt. Okay, so simplifying this, so we'll have d theta over dt is equal to, so we can write negative 5 in the numerator, and then x raised to negative 2 is 1 over x squared, so we can write x squared in the denominator. So x squared square root of 1 minus 5 over x squared, okay, times dx over dt. Okay, so now we can use to solve for d theta over dt, so we can now use the value of dx over dt and x. Okay, so we have dx over dt is equal to negative 2 meters per second, okay, and x is equal to 10 meters, okay, from the problem. Okay, so substitute, so d theta over dt is equal to negative 5, okay, over, we have 10 squared square root of 1 minus 5 over 10 squared times dx over dt is negative 2. So therefore, d theta over dt is equal to, so using our calculators again, so we have negative 5 over 10 squared square root of 1 minus open parenthesis, we have 5 over 10, oops, and then squared, right, and then outside multiplied by negative 2. So we have square root of 3 over 15. Yes. So in decimals, that would be 0.11547. Okay, so but I like to use this one, square root of 3 over 15. So square root of 3 over 15. So this unit, since this is the change of theta with respect to t, so this will be in radians per second. Okay, so that is now our rate of change of the angle. Okay, so as you can see, it is positive. So meaning, if it's positive, then the angle theta is increasing. Okay, so it's increasing. So if you try to imagine, so as the container gets nearer, so the angle between the ground and the cable increases. Okay, so it is positive. Okay, so the problem earlier, if we did not consider the sign of dx over dt, then what will happen is, if we neglect the negative sign here, so what will happen is our answer d theta will be, d theta over dt will be negative, right? And if it's negative, then that will mean that our rate of change of the angle is decreasing. Okay, so for which that is not consistent, okay, with our situation. So if we imagine, okay, so if we imagine what the situation would be, so the angle must be, the rate of the change of the angle must be positive. Okay, so that's some of the key points that you should be careful whenever you deal problems involving time rates. Okay, so that's it for this lesson, and then see you in the next videos.